Hello, let's talk about one-to-one functions and their inverses. So what I've written here for you is the definition of what a one-to-one function is. So that is a function, f is one-to-one if when f of x1 is equal to f of x2, then x1 equals x2. Now what this is saying is that whenever I have something that I'm plugging into the function, some x value, all right, that needs to result in one unique output, okay? So for example, if I plug in 1 and get out a number, then if I want to plug in a different number, I should not get that same value back that I got when I plugged in 1. And we'll see an example of it here in a second. There is a test that we can do graphically, and this test is called the horizontal line test. So, using this test, we can say that a function is one-to-one if and only if no horizontal line intersects the graph more than one time. Okay, so if you remember back when we were talking about functions, there was something called a vertical line test. And in this case, we're checking to see if the function is one-to-one. So now there's this horizontal line test, which we will see coming up here in just a minute. So let's take a look at a few examples to help get a better understanding of this. Okay, here is some examples to cover the topic that we just discussed about one-to-one functions. Here's two of them. Let's start with this first one. Is f of x equal to x cubed? This is our function here. Is that function one-to-one? Now we can show this graphically. I've drawn a graph here of f of x is equal to x cubed. This is the graph of it right here. Okay, it's just a sketch. It's not completely a perfect scale of that graph, but it looks like this. And these dotted lines I've drawn here represent the horizontal lines that I'm drawing through to check using the horizontal line test. If we look, every line that I'm drawing through this particular graph is only intersecting with this function at one exact point. At one exact point is its crossing. And because of that, because of the definition and the test that we just saw, we can say then that this is, in fact, a one-to-one function. So this one is a one-to-one function. Let's take a look at another example here. F of x is equal to x squared. Is this one-to-one? Is this function one-to-one? Well, let's do this in two ways. First off, the horizontal line test. Here is the graph of x squared. Now, if I try to draw a horizontal line through this, which I've denoted here with this, or represented here with this dotted line through, we see it intersects here and it intersects there. So if we remember back at the definition of this test and how it works, the line cannot intersect the graph in more than one place, which in this case it does. So that means it's not a one-to-one function. The horizontal test fails. But to kind of go and understand the definition as well, I went ahead and wrote down here, look what happens when we plug in 1. 1 squared, so if I plug in 1, I get 1 squared. And 1 squared, this is equal to 1. And then if I plug in negative 1, which would be negative 1 squared, this is also equal to 1. So this is saying now there are two x values, two inputs that produce the same output. And so because of that, we can also say that this is not a one-to-one function. Now let's look at some information about an inverse of a function. So here's the definition of the inverse of a function. We're going to let f be a one-to-one function. Now, it's very important for the inverse thing to work here. F needs to be one-to-one. Let f be a one-to-one function with domain A and range B. So these are our domain and ranges. Then the inverse, which is denoted by f of negative 1, that has the domain of B and the range of A. Notice that they have just switched places. So what that's saying here is, look, if I plug in x into my original function and get back y, then I can plug in y into my inverse and get back x. That's what this says right here. And you can go the other way around as well. So let's look at this example of how to find particular values, and this will illustrate this particular part of the definition right here. I've drawn this graph, and I put this dot here. Now we know this point is 2, 3. We could tell because of the x value here, and the y is 3 there. So if I try to figure out, when I plug in x, so when I plug in 2, what do I get as my output? And that would be 3. However, if I plug in if I take the inverse and plug in this output, then I get back x, what x was. So this is x and y, and notice now this is y and x. So if you're asked questions on, you're given, for example, f of x equals something, or f of 5 equals something, then you can take that thing and plug that in the inverse and get back 5. Okay? So hopefully that clears that up. Just remember, if f of x is equal to y, then you can plug in that y into the inverse and get back x. All right? Okay, let's go more into depth into some inverses and some particular properties as well. Okay, the inverse function property. All right, we're going to let f be 1 to 1, and it has a domain A and a range B. Okay? Now, this should look familiar here. This should look familiar here, right here. Especially this part. This is composite functions, which we talked about before. If I take my function itself and plug it into, as my input into the inverse, I get back x, and the same applies the other way around. The difference here is for every x is in A, in this case, and for every x in B. So let's take a look at this example right here, where f of x is equal to x cubed and g of x is equal to x to the 1/3. And the question says, show that these are inverses. All right. So what I can do is I can take g and plug in f. So here's g, and I'm going to take f and plug that in for the x there, which you can see then would be x cubed to the 1/3. Doing the laws of exponents here, we know we can multiply these together, and that gives us 1, so that equals x. So this is x to the 1. Similarly, if I go the other way around and take g and plug it into f, I get x cubed, x to the 1/3 is equal, x to the 1/3 cubed. And when I multiply through there again, it's the same thing, I get 1, so I also get x. So in both cases, I get x, like it says we should here, which means that these are, in fact, inverses of each other. So now, let's look at ways to find inverses of functions. Many types of questions that you'll see as a result of this section are going to ask you to find the inverses of functions, or find the inverse of functions, different ones. We're going to do 3 examples, but let's first look at these steps that are required in order to do this. The step 1 that we need to do is we need to take the function itself and replace f of x with y. That's what this is saying. So wherever I see f of x, I'm going to replace that with y. Then, everywhere I see an x, I'm going to swap it with a y, and everywhere I see a y, I'm going to swap that with an x. Then, we're going to solve for y, and finally, we're going to write y back as f of, but this time as f inverse of x. Okay? So write those steps down because we're going to use them every time in every example that we do in relation to how to find the inverse of a function. Let's start with a simple one. We have here f of x is equal to 3x minus 2. Well, step 1 says to write in y where I see f of x. So instead of f of x equals 3x minus 2, I now have y equals 3x minus 2. So I've completed step 1. Step 2 says to swap an x with a y and swap all y's with an x. So this one was a y, so now this one's an x. This one was an x, so now this one is a y. So now we've completed step 2. Step 3 says we solve for y. So let's do step 3. So step 3, what I can do is, I can just add this 2 over here. So if I add the 2 over, I get x plus 2 is equal to 3y. X plus 2 is equal to 3y because I added the 2 over. And then I can divide by 3. So now I get that x plus 2 over 3 is equal to y. So now I've gotten y by itself, which was asked to be done in step 3. And finally we can do step 4, which is replace this with the F inverse notation. Because we're used to seeing it in this form but it doesn't matter. You could have put x plus 2 equals 3 equals the inverse. You could have done it that way, but just for convention, I'm doing it this way. So now we've done step 4, and we found the inverse. So let's take a look at another example where we are increasing the complexity as we go. All right, here's the next example. F of x is equal to x to the 5th minus 3 all over 2. I'm not going to write steps down, step 1, step 2, like I did last time. We're just going to go through it. But I left the steps here so you can see that we're following them as we solve this problem. So first thing we're going to do, step 1 was to write it where it's y equals. So I've done that. Then I need to swap. Everywhere I see a y, I put an x, and everywhere I see an x, I put a y. Okay? Next up, we solve for y. So we're going to get y by itself here. The first thing I know we can do is we can multiply both sides by 2. This gives us 2x is equal to y to the 5th minus 3. Because now I'm moving that 2 over, and I can add the 3. That's another thing I can do next. And finally, we need to get rid of this 5th power on the y, so we can take the 5th root of both sides. All right, which gives us the 5th root is equal to y. So we've gotten y by itself, and then the next thing we have to do is we have to switch out the y with the inverse notation, which I will do right here. Inverse, F inverse is equal to the 5th root of 2x plus 3. And this is the answer, and it is the inverse to that. Now we can always check to make sure. We can just simply plug this in for x here, and we should get back x. I'll let you do that one on your own, but take this function and replace that where the x is here, and you should get back x when you do it. If you do, that means you found the inverse. All right? Okay, now let's take a look at an example of finding an inverse of a rational function. Okay, so here's a rational function that we have here. We're going to do the inverse. I have erased the steps, so hopefully you have those written down. I just need a little more room on this to do this one. But as we go, I'll write down what we're doing, and you can follow along. When it's a rational function, you're going to do this same process that we've been doing. But in addition to that, the steps that you'll take to solve it will match the steps that you take to solve any of these rational functions. So, because there are a couple of things that you have to do towards the middle of it that are a little not defined in those steps, but essentially it just involves solving for y. Okay, so first step, we put this down. Step one, of course we know. We're going to write it as y equals instead of f of x equals. So we replace the f of x with y. So that we've done. That's the first thing we have to do. The next thing we have to do is we need to replace every x with a y and every y with an x. Or we'll swap them. We swap them. You notice now this was originally y and these were originally x's. We've swapped them successfully. And now we can begin solving for y. So let's do that over here. So this is part 3. This is the bulk of the problem. Okay, so let's write down what we got. The first thing we're going to do is multiply both sides by y minus 1. We're just doing some algebra here. So when I do that, I get x times y minus 1 is equal to 2y plus 3. And the reason that we get that is if I multiply this side by y minus 1, those divide out to 1, they cancel out here, and then I'm left with the y minus 1 on this side. Alright? So we can say that that's what we're doing here. Y minus 1, I'm writing it small. We're multiplying both sides by that, and that's what we're left with right there. Because here, these would clear out. Okay, now we're going to distribute the left side. We're going to distribute the left side. So let's distribute. Let's distribute. This gives me xy minus x equals 2y plus 3. Alright? Notice that I just distributed this x into here and this x into this negative 1 to get that. Now here's the next part. If you can't see it, it just says anything that has a y in it goes to one side. And then likewise, anything that doesn't have a y in it goes to the other side. Well, I notice here, this has a y in it. Why don't I move this 2y over here and have moving this 2y over here. And then why don't I move this x over here so I'm left with this. So, now everything that has a y in it is on one side, and everything that doesn't have a y in it is on the other side. Just the basic algebra to get to this, you just have to do that part. So as you can see, that's what we have. That's what you want to have in all cases like this. You always want to have that. Let's see what's next. Next, we factor the y out. Factor out the y. So over here, I can now say that this is this. I've taken this y out of here. So I pulled the y out of there and I pulled the y out of there. What's left is x minus 2. If I redistribute this back in, I will have xy minus 2y again. So we factored that out right there. And now I can just get y by itself by simply dividing everything by x minus 2 here. Okay? I can divide everything by x minus 2 here. And what's left? Well, from this we can say that 3 gives us the result of y is equal to 3 plus x over x minus 2. Okay? Because these divide out to 1, and then that's what remains is what's over here. So it's y equals all of this. So we have that. And finally, the last part is we need to replace y with inverse function notation, which is here. Just wrote the same thing again, but except y is now the inverse of x. And this is the inverse. These were the steps that we took to get there. As you can see, there was some work there. Just do a couple practices of this. It's the same process every time. You're always going to multiply both sides by whatever's down here in the denominator when it's a rational function like this. Then you're going to end up doing some sort of distributing. It's going to happen. Then you're going to get all the y's on one side and all the non-y's on the other side. And then you're going to factor out the y and divide. These are the procedures that you will take in all questions like this. There are times where the inverse of a function is the same thing as the function. So where they're identical. That happens. And one other thing to know here that I didn't mention is make sure you understand the domain of this. In this case, x cannot equal -1. And down here, x can't equal -2. That's important to know. We got to make sure we define that those are not part of the domain of the function. So I didn't put it there, but I just did now. So now you know. If this was confusing for you, just watch it again and do a couple of your own examples. I will be posting several problems online that are like this. So you'll see a lot of them from me in the future, but this was just kind of the introduction to it. I hope you understood all of it, and I will see you next time.